Hi friends, this is Rashekar, a GATE faculty for electrical machines. In this video, let's see the basic principle of the transformer. The basic principle of the transformer. Let's see what is the basic principle of transformer actually. The basic principle of transformer is Faraday's laws of electromagnetic Faraday's laws of electromagnetic mutual induction. Faraday's laws of electromagnetic mutual induction is the basic principle of our transformer. Actually, to produce the EMF, whatever the machine, to produce the EMF, we must require requirements to produce EMF. What are the requirements to produce EMF? In that we have three main requirements. One is the set of conductors. And next one is the magnetic flux. And next one is the relative motion between these two. Relative motion between conductors and the flux. Actually, these relative motions are two types. In first case, if our conductors are stationary, nothing but zero speed. If the conductors are stationary, then the magnetic flux should be moving. Nothing but simply you have to give AC supply. And in next case, here, if the conductors are rotating nothing but dynamic in state. These are the stationary, these are the rotating. If the conductors are rotating, then magnetic flux should be, this is moving one, this is not moving one, nothing but DC flux, stationary flux. Here, this relative motion is called relative time variation. This is called relative time variation. And this is called relative space variation. Relative time variation and relative space variation. Okay? Here, see here conductors are stationary and the flux is moving. Then EMF induces. Here conductors are dynamic and flux is stationary. Then also EMF induces. But this induced EMF is called static induced EMF. This induced EMF is called static induced EMF because the conductors are stationary. This induced EMF is called dynamic induced EMF. This is called dynamic induced EMF because conductors are in dynamic state. And the best example for this phenomena is our transformer. Because for transformer, the conductors are stationary and we are giving the AC supply. We are giving the AC supply. Here, the best example is transformer. And here, the best example is generators. The best example is generators. Generators is the best examples for relative space variation. This is simple actually how the EMF induces. And here in relative time variation, the EMF induced in two ways. One is the self-induced, other one is the mutual induced. Self-induced and mutual induced. Let's see what is the self-induced and what is the mutual induced. For example, here I have two windings, one after one. See here, this is one winding, this is one winding, and this is another winding. This is another winding. Two windings are side by side. This winding having N1 number of turns and this winding having N2 number of turns. N1 number of turns and N2 number of turns. And next one, I am giving supply to the only one winding. I am giving supply to this winding. Supply, for example, some supply voltage V1 given to this winding which is called primary winding. When supply given to this winding, some current flows in the winding is called I1. When this current flows in the winding, it produces some flux is taken as phi1. Some flux produces phi1. Now, the EMF induced in these conductors, because these are the stationary conductors and I am giving the rotating magnetic field, nothing but this is the AC supply. I am giving the AC supply. Stationary winding and moving flux. Then EMF induces, that EMF is called self-induced EMF. Self-induced EMF. This EMF is equals to, this EMF is equals to minus N into minus N multiplied, here N nothing but primary winding turns N1, minus N1 d phi 1 upon dt, minus N1 d phi 1 upon dt. This is the self-induced EMF. For example, for small modification, see here I am doing a small modification, minus N1 d phi 1 by di1 and di1 upon dt multiplied and divided with di1. Now what we can say, n phi by I. N phi by I can be written as inductance L. The inductance of this winding, inductance of first coil L1, inductance of second coil L2. So this is a L1 into di1 by dt. This is the self-induced EMF of my winding. But this phi1 is also cuts with another beside winding also. This is the flux. It links with another winding also. It links with another winding also. When this flux links with this winding, again stationary conductors moving flux, again EMF induced in this winding. This EMF is called mutual induced EMF. This is also formula, mutual is equals to minus N multiplied with d phi upon dt, d phi upon dt. Again, for small modification, for easy calculations, see here, minus N2 minus N2 d∅1 upon di1 and di1 upon dt. But see here N1, phi1, I1. That's why this is L1. If it is N2, phi2, I2, then it may be L2. But here N2 is here, but here phi1 and I1, phi1 and I1, phi1 and I1. This is not clear, right? If all are ones, then L1. If all are twos, then L2. But here something is different here. Here is the second term and here two are the primary terms. This combination of these two, that is called the mutual inductance M12 or M21. First coil to the second coil to the first coil. Here this is written as the mutual inductance M. Mutual inductance M multiplied with di1 upon dt. This is the mutual induced EMF. Of course, this is M12, first coil to the second coil. If you write this, M12 is equals to N2 phi1 upon I1. If you want M21, tell me M21 is equals to N1 d phi2 upon di2. For example, this is equation A and this is equation B. Equation A and equation B. Then multiplied equation A and equation B once. Multiply those two. Then M1 to M21. M1 to M21 nothing but M into M. M into M. For example, M12 is equals to M21 is equals to M. Right? So what is this? What is this here? N2 phi1 I1. Right? Is equals to N2 phi1 I1. And what is this? N1 phi2 I2. N1 phi2 I2. Of course, if you take some constants k, for simplification, some constants k, coupling constants, this is coupling constant k square. The well-known formula m square is equal to k square into L2 into L1. Of course, m is equals to some constant k into L1, L2. Mutual inductance is equals to some coupling constant k multiplied with square root of L1, L2. This is a well-known formula for you. Just I giving you just simply brief analysis. So, what is mutual inductance and what is self-inductance? What is mutual induced EMF and what is self-induced EMF? You have to understand from this diagram, from this derivation. Of course, this is, you know that the mutual inductance M is equals to coupling factor K multiplied with the square root of self-inductance of the first coil and self-inductance of the second coil. This is simply what is mutual induction. From this, they will ask you questions now. What is the phase difference between supply voltage and induced voltage? They will ask you questions like this in competitive exams. So, in competitive exams, they will ask you questions like that. The angle or the phase difference, the phase displacement between supply voltage and induced voltage. Supply voltage and induced voltage is 180 degrees. The phase shift between input and output simply called as. the phase shift between supply voltage and induced voltage is 180 degrees. Sir, this is the primary induced voltage or secondary induced voltage? Of course, this is both, either primary or secondary, both are here only. Now the main question is that what is the angle between supply voltage and induced voltage is the first question, and what is the angle between supply voltage and primary induced voltage is the next question, and what is the angle between supply voltage and secondary induced voltage is the next question, and what is the angle between primary induced voltage and secondary induced voltage is the next question. Like that they will ask you questions. You tell me first what is the angle between supply voltage and induced voltage is 180 degrees, and is 180 degrees, and is 180 degrees, and is a both are in phase. Both are in phase. Remember this, the angle between primary induced voltage and secondary induced voltage is 0 degrees. 0 degrees. But the angle between EMF and the flux is the differentiation, nothing but 90 degrees. Differentiation, nothing but 90 degrees. Integration, nothing but 90 degrees. So the angle between EMF and the flux is 90 degrees only. 90 degrees only. So simply, what is the conclusion? The transformer operates on mutual induction. Of course, this is concluded. And next to conclusion, transformer is a phase shifting device. Transformer is a phase shifting device. Transformer having negative feedback. In which phase shift will take place? In positive feedback or negative feedback? In negative feedback, phase shift will take place. Transformer is a phase shifting device, and transformer having negative feedback. Transformer is a negative feedback circuit. This is the operation or the principle of transformer. Okay, so finally what is the conclusion? The basic principle is Faraday's laws of electromagnetic mutual induction. According to Faraday's law, the EMF induced in the transformer is, according to Faraday's law, the EMF induced in the transformer is directly proportional to rate of change of flux linkages. Directly proportional to rate of change of flux linkages. Nothing but the induced EMF, statically induced EMF is equals to the rate of change of flux linkages. Nothing but the induced EMF is directly proportional to N into d phi upon dt. This is the magnitude of EMF induced in the transformer. What about direction, sir? The direction, this is given for magnitude. This is for magnitude. This is for magnitude. Next for direction. The direction of induced EMF in the transformer given by Lenz's law. The direction given by Lenz's law. According to Lenz's law, every effect will opposes every effect will oppose its very cause. Every effect will oppose its very cause. What is the effect here? Here, effect is the induced EMF. And what is the cause here? The rate of change of flux linkages is the cause. So every effect will opposes its very cause. Every effect will opposes its very cause. E is equals to minus n into d phi by dt. This minus represents the opposite direction. According to Lenz's law, this minus represents the opposite direction. This is simply the basic principle of my transformer. This is the conclusion. Okay? Thank you.